Imagine opening your eyes aboard a spacecraft, decades into a journey that began before you were born. The vibrations of the engines have become the heartbeat you've known all your life. You drift to the observation window, press your hand against the cold glass, and look out into a darkness punctuated by unfamiliar stars. Earth is no longer visible, not even as a distant point of light. The sun that warmed your ancestors is just another star now, lost among thousands. And ahead, growing slowly brighter with each passing year, is a triple star system no human has ever witnessed up close. 3 suns dancing in gravitational embrace, surrounded by worlds we have only dreamed about. You are the first generation to see Alpha Centauri not through a telescope, but with your own eyes. This is not science fiction. This is the journey we must one day take if humanity is to become truly interstellar. Tonight, we turn our gaze toward the nearest stellar neighbor we have, Alpha Centauri, a system of 3 stars locked in an eternal cosmic waltz just over 4 light-years away. It is the closest star system to our own, the nearest shore across an ocean of darkness so vast that light itself, travelling at 186,000 miles per second, takes more than 4 years to cross it. To reach Alpha Centauri would be to accomplish something no civilization on Earth has ever attempted. It would dwarf the Apollo missions, the construction of the pyramids, even the centuries-long voyages of ancient explorers crossing unknown seas. This would be a journey measured not in years, but in generations, not in miles, but in the very limits of human endurance, creativity, and hope. Alpha Centauri represents more than just a destination. It represents possibility. It is close enough, astronomically speaking, that we can imagine reaching it. Far enough that doing so will require us to reinvent what it means to travel, to live, and to dream on timescales that stretch beyond individual lifetimes. Within its system may lie planets, perhaps even worlds with atmospheres, liquid water, conditions that echo the early Earth. Or perhaps we will find only barren rocks and frozen wastelands. Either way, the act of reaching out across the interstellar void would transform us, not because of what we find, but because of what we become in the effort. How long would it truly take to travel to Alpha Centauri? The answer is both humbling and inspiring. With current technology, tens of thousands of years. With experimental propulsion systems we are only beginning to understand, perhaps decades or centuries. The journey requires us to think beyond conventional rockets, beyond chemical fuels, and even beyond the physics that governs travel within our own solar system. It demands nuclear pulse engines riding the shockwaves of atomic detonations, laser-propelled light sails accelerating to a fraction of light speed, perhaps even technologies we have not yet conceived, fusion ramjets, that drink hydrogen from the interstellar medium, or antimatter engines that convert mass directly into thrust. Before we continue deeper into this journey, I'd like to ask you something. Wherever you are right now, whether you're drifting off to sleep under familiar stars or waking to a new morning, take a moment and let me know in the comments. Where are you watching from? What time is it where you are? It's comforting to know we're all sharing this voyage together, scattered across the globe, yet united by curiosity and wonder. Tonight, we will explore each method, each technology, each dream that could carry us across the interstellar dark. We will measure time not in hours, but in lifetimes. We will calculate distances that defy intuition and velocities that approach the cosmic speed limit itself. We will consider what it means to live aboard a starship, to be born in transit, to die before arrival, passing the mission on to children who will do the same. And we will ask ourselves, not if we can reach Alpha Centauri, but when and what we will become in the trying. So settle in. Let your thoughts expand beyond the familiar. Let us drift together toward the nearest stars and discover just how long it would take to touch them. Our voyage to Alpha Centauri begins now. When we speak of traveling to Alpha Centauri, we are not simply planning a longer version of our journeys to Mars or Jupiter. We are confronting a distance so vast, so fundamentally incomprehensible, that it challenges the very foundations of how we perceive travel itself. Alpha Centauri sits 37 light-years away from Earth, a measurement that translates to approximately 25.6 trillion miles. Yet these numbers, enormous as they are, fail to convey the true nature of what lies between us and our nearest stellar neighbour. Our human minds, evolved to understand distances measured in steps, miles, or at most the width of continents, are simply not equipped to grasp the genuine scale of interstellar space. To journey to Alpha Centauri is not merely to travel farther. It is to enter a realm where distance itself becomes something alien, where the familiar rules of movement dissolve into a cosmic vastness that stretches beyond imagination. The space between stars is not like the space between planets. It is not a gap to be crossed with patience and fuel. It is an ocean of darkness so profound that light itself, the fastest thing in existence, takes years to traverse it. Let us begin by attempting to make this distance tangible, to translate it into terms our minds can hold. Imagine, for a moment, that the Earth is reduced to the size of a single grain of sand, a tiny speck, barely visible, held between your fingertips. At this scale, the distance to our moon would be less than an inch. The Sun would sit about 2 feet away. Mars, at its closest approach, would be roughly 3 feet distant. Jupiter, the giant guardian of our solar system, would rest approximately 10 feet from our grain of sand Earth. Now, at this same scale, where would Alpha Centauri be? Not across the room, not across a building. Alpha Centauri would lie 4 miles away. 4 miles of empty space between one grain of sand and another distant point of light. This is the reality of interstellar distance. What separates us from our cosmic neighbours is not merely far, it is incomprehensibly, devastatingly far. When we consider our achievements in space travel thus far, the magnitude of this challenge becomes even more apparent. The International Space Station orbits Earth at an altitude of roughly 250 miles. The Moon, humanity's greatest journey to date, sits approximately 239,000 miles away. These distances, once considered the pinnacle of human ambition, are infinitesimal compared to the gulf that separates us from Alpha Centauri. If we placed every mile humans have ever travelled in space end to end, every orbit, every lunar mission, every probe sent to the outer planets, the total would not equal even a fraction of a percent of the distance to our nearest stellar neighbour. Our fastest spacecraft offers perhaps the most sobering perspective on this challenge. Voyager 1, launched in 1977, is currently the most distant human-made object in existence. It has left the solar system behind, crossing into the realm between stars, travelling at approximately 38,000 miles per hour relative to the Sun. This is an extraordinary speed by human standards, faster than anything we encounter in our daily lives, faster than sound, faster than the rotation of Earth itself. Voyager 1 has been traveling for decades, moving ceaselessly through the void, and yet, at its current velocity, it would take approximately 73,000 years to reach Alpha Centauri. 73,000 years. To place this in perspective, 73,000 years ago, modern humans were just beginning to migrate out of Africa. Written language did not exist. Agriculture had not been invented. The pyramids of Egypt would not be built for another 68,000 years. All of recorded human history, from the first civilizations to the present day, spans less than 1/10 of the time it would take Voyager 1 to reach Alpha Centauri. This is not a journey measured in human lifetimes. It is a journey measured in the rise and fall of civilizations, in evolutionary timescales, in epochs of geological transformation. And Voyager 1 represents our best, our fastest, our most ambitious effort to date. It is not struggling. It is not moving slowly by any reasonable measure. It is simply confronting a distance so vast that even unprecedented speed becomes glacial when measured against the void between stars. The ultimate speed limit in our universe is the speed of light itself, approximately 186,282 miles per second, or roughly 670 million miles per hour. Light from the Sun reaches Earth in just over 8 minutes. Light from Jupiter takes about 43 minutes to arrive. Yet light from Alpha Centauri, traveling at this cosmic speed limit, takes 37 years to complete its journey. This is not a flaw in light's velocity. It is a testament to the staggering emptiness that separates one star from another. Even at the fastest speed physically possible, the journey spans years, not hours or days. This fundamental limit shapes everything about interstellar travel. No matter what technology we develop, no matter what breakthroughs we achieve, we cannot exceed the speed of light. It is woven into the fabric of space-time itself, an absolute boundary set by the laws of physics. Any journey to Alpha Centauri, even using hypothetical technologies far beyond our current capabilities, will require years at minimum. There are no shortcuts through space, no hidden pathways that collapse distance. The void between stars is real, absolute, and uncompromising. The nature of interstellar space itself presents challenges that extend far beyond simple distance. The space between planets in our solar system, while vast, is not entirely empty. It contains particles from the solar wind, magnetic fields, occasional asteroids, and the faint glow of zodiacal dust. But the space between stars is different. It is a darkness so complete, so devoid of matter, that a traveller could drift for years without encountering anything larger than a molecule. The silence here is absolute. The isolation is total. There are no landmarks, no reference points, nothing but the distant, unchanging stars to mark the passage of time. This emptiness is both a challenge and an opportunity. On one hand, there's nothing to slow a spacecraft down, no atmospheric drag, no gravitational interference from nearby bodies. Once accelerated, a vessel could coast indefinitely, its speed unchanging across the light years. But this same emptiness means there is also nothing to help. No planets to use for gravity assists, no resources to harvest, no emergency stops if something goes wrong. A spacecraft bound for Alpha Centauri must carry everything it needs for the entire journey: fuel, supplies, spare parts, all while maintaining functionality across timescales that dwarf any engineered system ever built. Traditional rocket propulsion, the foundation of all space travel to date, becomes not just impractical, but absurd at interstellar distances. Rockets work by expelling mass at high velocity, creating thrust through Newton's third law. To travel faster or to travel farther, a rocket must carry more fuel. But fuel itself has mass, which means more fuel is needed to accelerate that fuel, which means even more fuel is needed to accelerate the fuel that accelerates the fuel. This is the tyranny of the rocket equation, and it grows exponentially worse as desired speeds increase. To reach even a fraction of the speed of light using conventional chemical rockets would require a fuel mass many thousands of times greater than the mass of the spacecraft itself. Some calculations suggest that to accelerate a modest probe to just 10% of light speed using traditional rockets, the fuel tank would need to be larger than a planet. This is not an engineering challenge. It is a physical impossibility. Rocket propulsion, so successful for reaching orbit and traveling within our solar system, simply cannot bridge the gap between stars. The energy requirements tell the same story from a different angle. The kinetic energy of an object increases with the square of its velocity. Doubling your speed requires 4 times the energy. Tripling, it requires 9 times the energy. To reach speeds necessary for reasonable interstellar travel, tens of thousands or even hundreds of thousands of miles per second, the energy requirements become astronomical. We are not speaking of energy measured in kilowatt hours or megawatt hours, but energy approaching the total output of stars themselves. The energy contained in all the chemical fuels on Earth would barely accelerate a small probe to a meaningful fraction of light speed. This is the fundamental barrier that separates planetary exploration from interstellar travel. Within our solar system, distances are vast but manageable. Journeys take months or years, not millennia. Speeds measured in thousands of miles per hour are sufficient. But between stars, these same approaches fail completely. The distances are too great, the speeds too slow, the energy too immense. We cannot simply build bigger rockets or pack more fuel. We must rethink the very concept of propulsion itself. Our entire human experience with spaceflight spans mere hundreds of miles above Earth's surface. Astronauts aboard the International Space Station orbit at an altitude of about 250 miles. The Moon, our farthest human destination, sits less than 250,000 miles away. Even these journeys, celebrated as triumphs of human achievement, represent the tiniest fraction of interstellar space. If the journey to Alpha Centauri were a marathon, our furthest travels would not have taken us past the starting line. They would not have taken us to the edge of the stadium. We would still be standing in the parking lot, contemplating the impossible distance ahead. Yet this vast distance, this incomprehensible gulf between stars, is not an ending, but a beginning. It is a reminder that the universe operates on scales far beyond human intuition, that the cosmos is not built for our convenience, but according to laws written in mathematics and physics. To reach Alpha Centauri is to accept that we must evolve beyond the methods that brought us this far. We must discover new forms of propulsion, new sources of energy, new ways of thinking about motion and time. The distance to Alpha Centauri is not merely a number. It is a question posed by the universe itself. Are we capable of thinking beyond the limits of our experience? Can we build vessels that endure for centuries? Can we harness energies so vast they seem like magic? The answer lies not in the stars above, but in our willingness to transform the impossible into the inevitable. As we stand at the edge of interstellar space, peering across the light years toward Alpha Centauri, We are no longer simply asking how long it would take. We are asking what kind of species we must become to make the journey at all. And in that question lies the true measure of distance, not in miles or light years, but in the gap between what we are and what we must be to touch another star. We have sent spacecraft to the Moon, to Mars, and beyond the edge of our solar system. We have harnessed chemical fire, nuclear power, and the subtle push of ions accelerated through electromagnetic fields. Yet when we turn our instruments toward Alpha Centauri and ask the simple question, how long would it take us to get there with the technology we possess today? The answer is not measured in years or even decades. It is measured in millennia, in epochs, in timescales so vast they dissolve the very meaning of a human journey. The rockets that carried us to the Moon, the mighty Saturn V and its descendants, represent some of humanity's greatest technological achievements. They propelled us across nearly 240,000 miles of space in just 3 days, a feat that seemed impossible mere decades before it happened. Chemical propulsion, the burning of fuel and oxidizer to create thrust, is powerful, reliable, and well understood. It is the foundation of every crewed mission we have ever flown. But when we apply this same technology to interstellar distances, the numbers become sobering, almost incomprehensible. A conventional chemical rocket traveling to Alpha Centauri would take between 19,000 and 81,000 years to complete the journey. To put this in perspective, 19,000 years ago, humanity had not yet invented agriculture. We lived in small tribes, carved tools from stone, and painted stories on cave walls. The oldest known writing systems would not emerge for another 14,000 years. 81,000 years ago, our species was barely established on Earth, still sharing the planet with other human species that would eventually vanish into extinction. These are not journeys. They are geological eras compressed into a single mission profile. The reason for these staggering timescales lies in the fundamental physics of chemical propulsion. Rockets work by expelling mass at high velocity, and the maximum speed they can achieve is limited by the exhaust velocity of their propellant. For chemical rockets, this exhaust velocity is constrained by the energy released in chemical reactions, typically producing speeds of around 4 to 5 kilometers per second. To reach Alpha Centauri in a human lifetime, we would need to travel at least 10% the speed of light, roughly 30,000 kilometers per second. Chemical propulsion cannot bridge this gap, not with incremental improvements, not with better engineering. The laws of chemistry themselves stand in the way, and so we look to more advanced systems, technologies that exist today, but have only been deployed on robotic missions. Ion drives and electric propulsion systems represent a significant leap forward. Unlike chemical rockets that burn fuel in explosive bursts, ion drives accelerate charged particles using electromagnetic fields, expelling them at velocities up to 10 times greater than chemical exhaust. The thrust is gentle, almost imperceptible, but it is continuous. Over months and years, an ion drive can accelerate a spacecraft to speeds that chemical rockets cannot match. NASA's Dawn mission used ion propulsion to explore the asteroid belt, visiting both Vesta and Ceres with remarkable efficiency. The European Space Agency's Bepi Colombo mission to Mercury relies on similar technology. These spacecraft prove that ion drives work, that they can operate for years without failure, gradually building velocity through patient, persistent acceleration. If we were to send an ion-powered probe to Alpha Centauri, the journey time would drop significantly compared to chemical rockets. Estimates suggest it could reach the star system in 18,000 to 36,000 years. This is progress, but it remains progress measured against eternity. Even at the upper end of ion propulsion capability, we are still talking about a journey lasting 360 centuries. Entire civilizations would rise and fall on Earth while the spacecraft drifted through the void. Languages would evolve beyond recognition. Technologies we cannot yet imagine would be invented, deployed, and rendered obsolete. The people who launched the mission would be forgotten ancestors to those who might, perhaps, receive its first transmissions from another star. Then there is nuclear thermal propulsion, a technology that has been tested, studied, and nearly deployed multiple times throughout the space age. Nuclear thermal rockets work by heating a propellant, typically hydrogen, using a nuclear reactor, then expelling it through a nozzle at extremely high speeds. The exhaust velocity is roughly twice that of chemical rockets, and the energy density of nuclear fuel is vastly superior. In the 1960s and 70s, NASA's NERVA program successfully tested nuclear thermal engines that could have sent astronauts to Mars in a fraction of the time required by chemical propulsion. The technology works. It is real. It is achievable with today's engineering. If we applied nuclear thermal propulsion to an interstellar mission, the travel time to Alpha Centauri could potentially be reduced to somewhere between 10,000 and 20,000 years. This is a considerable improvement, cutting the journey time roughly in half compared to chemical or rockets. But even this represents a span of time that defies human comprehension. 10,000 years ago, the last ice age was ending. Humans were beginning to domesticate animals and cultivate the first crops. Writing did not exist. Cities did not exist. The entire recorded history of human civilization spans only the last 5,000 years. A nuclear thermal mission to Alpha Centauri would take twice that long. To understand what these timescales truly mean, we can look at the Voyager probes, humanity's most distant ambassadors. Launched in 1977, Voyager 1 and Voyager 2 have travelled farther from Earth than any other human-made objects. Voyager 1 is now more than 15 billion miles away, moving through interstellar space at roughly 38,000 miles per hour. It is fast by any terrestrial standard, but on cosmic scales, it is achingly slow. If Voyager 1 were headed directly toward Alpha Centauri, which it is not, it would take more than 70,000 years to arrive. And Voyager represents the pinnacle of what we have actually achieved. Not theoretical designs, but real spacecraft flying through real space at real speeds. The fundamental problem with all conventional propulsion methods is encapsulated in the tyranny of the rocket equation. To go faster, a rocket must carry more fuel. But more fuel means more mass, which requires even more fuel to accelerate. The relationship is exponential and unforgiving. For a mission to Alpha Centauri using conventional propulsion, the fuel requirements quickly become absurd. Even with the most optimistic assumptions about nuclear thermal or ion propulsion, the fuel mass needed would dwarf the payload by factors of millions or billions. We would be building fuel tanks with tiny spacecraft attached, and even then, the journey would span hundreds of generations. This leads us to one of the most haunting concepts in all of space exploration, the generational ship. If we cannot reach Alpha Centauri in a single human lifetime, Perhaps we could build a spacecraft large enough to sustain a small population across multiple lifetimes. A vessel that is not just a machine, but a world unto itself. A self-contained ecosystem drifting through the void, carrying within it an entire society that would live, love, reproduce, age, and die, knowing that neither they, nor their children, nor their children's children would ever see the destination. Only some distant descendant, thousands of years hence, might finally witness the light of a new sun. The concept is both inspiring and deeply unsettling. A generational ship would need to support hundreds or thousands of people for millennia. It would require closed-loop life support systems that could recycle air, water, and nutrients with near-perfect efficiency for thousands of years. It would need artificial gravity to prevent bone loss and muscle atrophy. It would need vast stores of genetic diversity to prevent inbreeding. It would need infrastructure to manufacture replacement parts for systems that would inevitably fail. It would need to be a garden, a hospital, a school, a factory, and a cemetery, all enclosed within metal walls, surrounded by infinite darkness. But the engineering challenges, as daunting as they are, pale in comparison to the psychological and biological realities. What would it mean to be born aboard such a vessel? To grow up knowing that your entire life would be spent in corridors and chambers, with no horizon, no sky, no wind? How would a society maintain purpose and cohesion across centuries when the original mission, the reason for existence, becomes an abstract historical fact rather than a lived reality? What happens when generations 300 or 500 begin to question why they should continue a journey they did not choose, toward a destination they will never see? There is no ocean crossing, no desert trek, no historical migration that offers a precedent. The Polynesian navigators who settled the Pacific Islands travelled for weeks or months, not millennia. The generation that set out from Tahiti could still tell their children about the land they left behind. On a journey to Alpha Centauri spanning 10,000 years, Earth itself would fade into mythology. No one aboard the ship would have any living connection to humanity's homeworld. It would become a story, then a legend, then perhaps a half-remembered dream. Biologically, the challenges are equally profound. Radiation exposure in deep space is relentless. Without Earth's magnetic field and atmosphere to shield them, the crew would be constantly bombarded by cosmic rays and solar particles. Over generations, this could lead to increased cancer rates, genetic mutations, and biological damage we cannot yet predict. Medical technology would need to advance far beyond our current capabilities, not just to treat disease, but to potentially edit the human genome to adapt to the conditions of interstellar space. We might arrive at Alpha Centauri no longer quite human, transformed by the journey itself into something new. And then there is the question of propulsion maintenance. A journey of 10,000 years means 10,000 years of systems operation without external support. No resupply missions, no rescue. If the reactor fails, if the life support falters, if a micrometeorite punctures the hull in a critical location, the mission ends. Everyone dies. The ship becomes a tomb, a coffin drifting silently through the void, carrying the remains of an entire lineage of explorers who gambled everything on a destination they would never reach. All of these considerations bring us to an inescapable conclusion. Conventional propulsion, even at its most advanced, is not a viable path to the stars. Not for crewed missions, not for any mission we would want to launch with the intention of receiving results within the lifetime of our civilization. Chemical rockets, ion drives, and nuclear, thermal engines have taken us to the Moon, to Mars, and to the outer planets. They have expanded our understanding of the solar system immeasurably, but they are tools designed for planetary distances, not interstellar gulfs. Alpha Centauri is not merely far. It is far in a way that breaks conventional transportation. The distance is not just quantitatively larger, it is qualitatively different. It exists in a regime where the assumptions underlying rocket propulsion, burning fuel to gain speed, carrying that fuel as payload mass, cease to be meaningful. To reach the stars, we need to think beyond propulsion as we have always known it. We need to imagine methods that do not rely on carrying fuel, that do not require thousands of years, that do not demand the sacrifice of countless generations. As we contemplate these vast timescales and impossible requirements, we begin to understand why interstellar travel has remained the domain of science fiction for so long. It is not because we lack ambition or curiosity. It is because the universe itself imposes barriers so immense that incremental improvements in rocket technology will never be sufficient. We have reached the limits of convention. The next step requires something radical, something that abandons the paradigm of burning fuel and expelling mass, and embraces entirely new principles of motion and energy. The journey to Alpha Centauri will not be made with better rockets. It will be made, if it is made at all, with technologies that harness forces we are only beginning to understand. Technologies that sound more like fantasy than engineering. But before we dismiss them as impossible, we must remember that ion drives once seemed fantastical, that nuclear propulsion was once the realm of dreamers, that the very idea of leaving Earth's atmosphere was considered absurd by serious scientists just over a century ago. We stand now at the threshold, not of a solution, but of a realization. Conventional propulsion has taken us as far as it can. The next leap will require us to think not like rocket engineers, but like physicists, explorers of fundamental forces, architects of methods that do not yet exist. And so we turn our attention away from chemical flames and ion streams, and toward ideas that once lived only in the pages of speculative fiction, but are now entering the realm of serious scientific consideration. Ideas that might, just might, allow us to touch another star not in 10,000 years, but in a single human lifetime. Conventional rockets brought us to the Moon. They have carried our robotic emissaries across billions of miles. But to reach Alpha Centauri within a human lifetime, we must think beyond chemical fuel and traditional engines. We must consider methods that sound like science fiction, yet rest firmly on the foundations of physics. Among these audacious concepts, one stands out for its sheer boldness, its elegant brutality, and its surprising feasibility. Nuclear pulse, propulsion. The idea of riding controlled atomic explosions across the void of space. This is not fantasy. This is engineering conceived by brilliant minds in the 1950s and 60s, calculated with precision, tested in laboratories, and deemed not just possible, but practical. It is a method so powerful it could accelerate a spacecraft to velocities conventional rockets can only dream of, cutting our journey to Alpha Centauri from tens of thousands of years to mere decades or centuries. And yet, it requires us to embrace something profound and unsettling, that the same forces capable of devastating cities might be the key to unlocking the stars. The concept at the heart of nuclear pulse propulsion is deceptively simple. Instead of burning fuel to create thrust, a spacecraft would eject nuclear bombs behind itself at regular intervals, detonating each one in rapid succession. The explosion would strike a massive shock absorber plate at the rear of the craft, transferring momentum and propelling the ship forward. Explosion after explosion, pulse after pulse, the spacecraft would accelerate, each detonation adding velocity until the ship is traveling at a significant fraction of the speed of light. This was Project Orion, conceived in the late 1950s by physicist Freeman Dyson and a team of visionaries at General Atomics. Their calculations were not speculative dreams. They were grounded in the known physics of nuclear weapons and engineering materials. The design called for a spacecraft weighing thousands of tons, equipped with a pusher plate made of steel and other ablative materials capable of withstanding the hellish forces of repeated nuclear blasts. Between the plate and the ship, enormous shock absorbers would cushion the crew from the violent pulses, transforming raw explosive energy into smooth, continuous acceleration. The numbers were extraordinary. Project Orion could theoretically propel a spacecraft to speeds between 3 and 5% the speed of light. At such velocities, the journey to Alpha Centauri would take between 85 and 130 years, not a single human lifetime, but within the scope of a multi-generational mission. Suddenly, interstellar travel shifted from the realm of impossibility into the domain of extraordinary but achievable engineering. Imagine the experience aboard such a vessel. Every few seconds, another nuclear device is ejected from the rear of the ship. A brief moment passes. Then the explosion. A flash of light brighter than the sun itself, expanding in a perfect sphere of plasma and radiation. The shockwave hits the pusher plate with unimaginable force. The entire spacecraft lurches forward. The shock absorbers compress, massive pistons designed to turn catastrophic force into controlled momentum. Inside the crew compartment, astronauts feel a steady, rhythmic pulse. Not the gentle hum of chemical rockets, but the heartbeat of atomic fire, propelling them ever faster through the cosmic night. This is not gentle travel. This is not the serene glide of science fiction films. This is raw, violent, relentless acceleration, powered by humanity's most destructive technology, transformed into our greatest tool of exploration. Each pulse adds meters per second to the ship's velocity. Hour after hour, day after day, the bombs continue. Thousands of nuclear devices, each carefully timed, each perfectly positioned, each adding to the accumulating speed until the spacecraft is moving so fast that the stars themselves begin to shift in the windows, distorted by relativistic effects. The engineering challenges are immense, but not insurmountable. The pusher plate must endure temperatures exceeding those found on the surface of stars, if only for milliseconds at a time. Material science in the 1960s already suggested that certain alloys could survive. Modern advances in heat-resistant ceramics, carbon composites, and ablative materials make the concept even more viable today. The shock absorbers must cushion forces equivalent to hundreds of Gs, down to levels humans can tolerate, perhaps 1 or 2 Gs of constant acceleration. This is ambitious, but within the boundaries of known engineering. What made Project Orion truly remarkable was that scientists in the 1950s and 60s took it seriously. This was not idle speculation. Engineers built models. They conducted small-scale tests using conventional explosives to validate the physics. In 1959, a 1-meter test vehicle nicknamed Put-Put successfully demonstrated the concept, propelled upward by a series of chemical explosions. The physics worked. The principle was sound. Nuclear pulse propulsion was not a question of if it could work, but when humanity would be ready to build it. Yet for all its promise, Project Orion faced obstacles that had nothing to do with engineering. The first was political. In 1963, the Partial Nuclear Test Ban Treaty prohibited nuclear explosions in the atmosphere, underwater, and in outer space. The treaty was essential for preventing the escalation of the nuclear arms race, but it also closed the door on nuclear pulse propulsion as originally envisioned. To launch an Orion spacecraft from Earth's surface would require detonating hundreds of nuclear devices in the atmosphere, an unthinkable proposition in an era already fearful of radioactive fallout. The second obstacle was psychological and ethical. The public recoiled at the idea of using nuclear weapons for any purpose, even exploration. The very technology that could carry us to the stars was the same technology that cast a shadow of annihilation over civilization. How could humanity justify building a spacecraft powered by atomic bombs when those same bombs threatened our existence? The dream of riding nuclear fire to Alpha Centauri became entangled with the nightmare of nuclear war, and so Project Orion was shelved. Not because it couldn't work, but because the world was not ready for it. Funding dried up. Research halted. The blueprints were filed away, relics of an audacious era when scientists dared to imagine harnessing destruction for creation. But ideas, once born, do not die easily. In the 1970s, a new generation of scientists revisited the concept under a new name, Project Daedalus. Sponsored by the British Interplanetary Society, Daedalus proposed a refinement. Instead of using fission bombs like those in Project Orion, Daedalus would use fusion reactions, cleaner, more efficient, and less politically contentious. Small pellets of deuterium and helium-3 would be ignited by powerful electron beams, creating miniature thermonuclear explosions that would propel the spacecraft forward. The principles remained the same: pulsed detonations, massive thrust, and velocities approaching a significant fraction of light speed. But fusion offered advantages. The fuel was denser in energy. The radiation produced was less harmful, and crucially, fusion propulsion did not violate international treaties in the same way fission bombs did. Project Daedalus envisioned an unmanned probe reaching Barnard's star 6 light-years away in just 50 years. Though never built, Daedalus demonstrated that nuclear pulse propulsion could evolve, adapt, and remain viable as our understanding of physics and materials advanced. The resource requirements for such a mission are staggering, but not impossible. To reach Alpha Centauri using nuclear pulse propulsion would require thousands of nuclear devices, each carefully engineered and precisely detonated. Project Orion's original designs called for 800 bombs just to escape Earth's gravity, and tens of thousands more to reach interstellar velocities. The logistics are daunting. Manufacturing, storing, and managing such an arsenal would be one of the greatest industrial undertakings in human history. Yet consider the alternative. Chemical rockets require exponentially more fuel for every increment of speed. Ion drives, though efficient, take decades to reach even modest velocities. Nuclear pulse propulsion, for all its explosive drama, is surprisingly practical. The energy density of nuclear reactions is unmatched. A single kilogram of uranium or deuterium contains millions of times more energy than a kilogram of chemical fuel. In the cold calculus of interstellar travel, riding atomic explosions is not reckless. It is logical. Modern scientists continue to explore variations of the concept. Instead of external detonations, some designs propose internal fusion reactions contained within magnetic fields, channeling the energy through exhaust nozzles. Others suggest using antimatter catalyzed fusion, where tiny amounts of antimatter trigger larger fusion reactions, reducing the amount of exotic fuel needed. Each iteration refines the original vision, making it safer, more efficient, and more politically palatable. What remains constant is the recognition that reaching the stars requires energies on scales we have only encountered in weapons. The sun itself is a fusion reactor, releasing energy through the same processes we seek to harness for propulsion. Nuclear pulse propulsion forces us to confront an uncomfortable truth. The boundary between destruction and creation is not as clear as we might wish. The same reactions that power stars and devastate cities can carry us to other worlds, if only we have the wisdom and courage to use them responsibly. As we imagine a spacecraft accelerating through the darkness, propelled by pulses of nuclear fire, we are reminded that exploration has always demanded audacity. Crossing oceans required sailing into the unknown. Reaching the moon required riding controlled explosions. Touching another star may require us to embrace forces we have long feared, transforming instruments of war into engines of discovery. Nuclear pulse propulsion stands as a testament to human ingenuity and paradox. It is a method both violent and elegant, terrifying and inspiring, abandoned yet never forgotten. In the quiet of space, far beyond the reach of treaties and politics, perhaps one day a spacecraft will pulse its way toward Alpha Centauri, each detonation a drumbeat of human ambition, each flash of light a declaration that we are willing to harness even the atom's fury to fulfill our destiny among the stars. The journey would still take decades, perhaps more than a century, but compared to the tens of thousands of years required by conventional means, nuclear pulse propulsion transforms interstellar travel from impossible to merely extraordinarily difficult. And in the vastness of space, where distance is measured not in miles, but in the endurance of civilizations, that difference is everything. Beyond rockets and nuclear pulses, beyond even the dreams of fusion drives, there exists a concept so elegant it seems almost too simple to work. What if, instead of carrying fuel at all, we could ride upon light itself? What if the answer to crossing interstellar space was not to push harder, but to push lighter, to strip away everything except the essential, and let the universe's fastest messenger carry us to the stars? This is the vision of Breakthrough Starshot, a proposal that reimagines everything we thought we knew about space travel. It asks not how we can make our spacecraft faster, but how we can make them so small, so light, that even the gentle pressure of photons becomes a mighty wind capable of propelling us across the cosmic ocean. The concept is radical in its simplicity. Instead of building massive starships laden with fuel and engines, we create spacecraft no larger than a microchip, weighing only a few grams. These tiny probes would be attached to ultra-thin reflective sails, gossamer sheets of material just atoms thick, designed to catch and ride upon beams of laser light. From Earth, we would construct an array of powerful lasers, perhaps spanning miles, capable of generating hundreds of gigawatts of focused energy. When activated, this laser array would lock onto the sail and push, not with physical contact, but with the momentum of pure light. In those first moments of acceleration, something extraordinary would occur. The spacecraft would begin moving, slowly at first, then faster still. Within minutes, it would be traveling at speeds that would take conventional rockets years to achieve. Within hours, it would surpass anything humanity has ever launched. And within days, if the laser could maintain its focus and power, the tiny probe could reach 20% the speed of light, approximately 134 million miles per hour. At such velocities, the journey to Alpha Centauri transforms from an impossibility into a merely extraordinary challenge. What would take conventional spacecraft tens of thousands of years could be accomplished in just 20 to 30 years. A single human lifetime. A parent could watch the launch and live to receive the first images from another star system. The gulf between solar systems, once an unbridgeable void, suddenly becomes traversable within the span of a generation. This vision captured the imagination of some of the greatest minds of our time. The late Stephen Hawking, alongside entrepreneur Yuri Milner and a coalition of scientists and engineers, announced breakthrough Starshot in 2016, calling it humanity's most realistic near-term path to reaching the stars. Their endorsement was not born of fantasy, but of careful calculation. The physics, they argued, is sound. The technology, while challenging, requires no new laws of nature, no undiscovered particles, no miracles. Everything needed to make this work either exists or lies just beyond our current engineering capabilities. The spacecraft itself would be a marvel of miniaturization. Imagine a device smaller than a postage stamp, yet containing cameras, power systems, navigation instruments, and communication equipment. Advances in nanotechnology and microelectronics have made such devices conceivable. Modern smartphones contain more computing power than the spacecraft that carried astronauts to the moon. Now, compress that technology further, strip away everything non-essential, optimize every circuit and sensor for minimal mass and maximum efficiency. What remains is a star chip, a gram-scale probe carrying humanity's eyes and instruments into the interstellar darkness. The sail itself would be equally extraordinary. Constructed from materials like graphene or other advanced metamaterials, it would need to be incredibly light, yet strong enough to withstand the intense pressure of laser light without tearing or warping. The sail might measure several meters across, yet weigh no more than a few grams, thinner than a soap bubble, more reflective than the finest mirror. When deployed in space, it would shimmer like a gossamer wing, waiting to catch the wind of artificial starlight. But the true engineering challenge lies not in space, but on Earth. The laser array required to accelerate these probes would be unlike anything ever constructed. Current proposals envision a phased array of lasers, possibly covering square kilometers of ground, working in perfect synchronization to generate a single coherent beam. The power requirements are staggering, potentially requiring gigawatts of energy, equivalent to the output of several large power plants, all focused into a beam narrow enough to strike a target no larger than a sailboat, accelerating rapidly into the distance. This array might be built on Earth, perhaps in a high desert or on a mountain peak where the atmosphere is thin and clear. Or it might be constructed in space itself, orbiting high above the planet, free from atmospheric distortion, able to direct its energy with perfect precision. Either way, the technological demands are immense. The lasers must maintain their focus across distances that grow from thousands of miles to millions, then billions, then trillions. They must track the accelerating probe with perfect accuracy, compensating for the Earth's rotation, the probe's trajectory, and the countless distortions that light encounters as it travels through space. Even with perfect aim, physics imposes its own constraints. As the probe accelerates away from Earth, the laser beam naturally spreads, its energy dissipating across an ever-widening cone. By the time the probe reaches the outer solar system, the beam may be millions of miles wide, its intensity reduced to a whisper. This is why acceleration must happen quickly, within the first hours or days, while the probe is still relatively close, and the laser can maintain sufficient intensity to push effectively. Once the laser can no longer reach the probe, the acceleration stops. From that moment forward, the spacecraft coasts, carried by nothing but the velocity it gained during those intense hours of illumination. There is no engine to restart, no fuel to burn, no way to speed up or slow down. The probe becomes a silent projectile, hurtling through the void at a fifth the speed of light, bound for Alpha Centauri on a trajectory that cannot be altered. This immutability presents one of breakthrough Starshot's greatest limitations. The probe cannot slow down when it reaches its destination. There is no fuel for deceleration, no atmosphere to create drag, no gravitational body massive enough to capture something moving so fast. When the probe finally arrives at Alpha Centauri after 2 decades of flight, it will flash through the system in mere hours or days, its cameras and sensors frantically gathering data as stars, planets and moons rush past at relativistic speeds. Then, just as quickly, it will be gone, disappearing into the darkness beyond, continuing its eternal voyage through the galaxy with no possibility of return. Yet even a fleeting encounter would be revolutionary. In those brief hours of passage, the probe could capture images and data that would transform our understanding of neighboring star systems. Are there planets orbiting Alpha Centauri stars? Do any harbor conditions suitable for life? What does an alien solar system look like up close? Questions that have haunted humanity since we first gazed at the stars could finally receive answers, transmitted back to Earth across the light years as faint whispers of radio waves. The communication challenge itself is formidable. At a distance of 4.37 light years, even a message traveling at light speed takes over 4 years to reach home. The probe's tiny transmitter, powered perhaps by a miniature radioactive battery or harvesting trace amounts of ambient radiation, must broadcast with enough strength for Earth's most sensitive radio telescopes to detect its signal amid the cosmic background noise. Every photograph, every measurement, every byte of data must be carefully encoded and transmitted, then received years later by scientists who may have spent decades waiting for this moment. The timeline for achieving breakthrough Starshot is ambitious, yet grounded in realistic projections. The technology required, while advanced, does not violate known physics. With sufficient funding and international cooperation, the first test launches could occur within a few decades. The laser array might be completed within 30 to 50 years, assuming steady progress in laser technology, materials science, and space infrastructure. The first actual mission to Alpha Centauri could launch within 50 to 100 years and return its first images 70 to 130 years from now. This makes Breakthrough Starshot unique among interstellar proposals. It is not a distant dream relegated to science fiction, but a genuine possibility that could be realized within the lifetimes of children being born today. No other current proposal offers such a combination of achievable technology and realistic timelines. It represents not the distant future of space exploration, but its near horizon, the next great leap waiting just beyond our current capabilities. Standing at the edge of this possibility, we confront profound questions about exploration itself. For millennia, human explorers ventured into unknown lands with the expectation of return, of bringing back not just knowledge, but their own experiences, their stories, themselves. Breakthrough Starshot asks us to accept a different kind of exploration, one where our ambassadors are eternal voyagers, small silent witnesses that will never come home, never share their journey except through the data they transmit across the infinite dark. Yet perhaps this is the only way. Perhaps the stars can only be reached by those willing to let go, to send forth fragments of our curiosity and creativity, miniaturized and multiplied, cast like seeds into the cosmic wind. If we cannot go ourselves, not yet, we can send our eyes and instruments, our questions and our wonder, carried on, beams of light toward distant suns. Breakthrough Starshot reminds us that space travel is not only about brute force and massive engines. Sometimes the answer lies in elegance, in working with nature's fundamental forces rather than against them. Light has traveled from distant galaxies to reach our eyes across billions of years. Now, we propose to harness that same force, to ride upon its momentum, to let photons carry us where chemical rockets never could. The vision is both humbling and exhilarating. These tiny probes, each weighing less than a hummingbird's feather, could accomplish what entire fleets of conventional spacecraft cannot. They could make humanity an interstellar species not through conquest or colonization, but through presence, through the simple act of arriving, of bearing witness, of reaching across the darkness to touch another sun. As we contemplate this possibility, we realize that the journey to Alpha Centauri is not merely about distance, but about reimagining what is possible when we surrender our assumptions and embrace radical simplicity. The stars are far, impossibly far by human standards, but light crosses those distances every day. And if we can learn to ride upon that cosmic tide, carried by artificial starlight toward natural suns, then perhaps the stars are not so unreachable after all. Perhaps they are simply waiting for us to become light enough to reach them. Beyond lasers and light sails, beyond nuclear pulses and chemical rockets, there exist propulsion concepts so ambitious they seem to belong not to science, but to dreams. Yet they rest upon real physics, theoretical frameworks that challenge the very limits of what matter and energy can achieve. As we contemplate crossing the void to Alpha Centauri, we must venture into the realm of technologies that do not yet exist but could, given time, ingenuity, and a profound transformation of our relationship with the universe itself. Here, at the frontier of imagination and physics, we encounter fusion ramjets and antimatter propulsion, systems that could reshape the journey from a multi-generational odyssey into a voyage measured in years, perhaps even a single human lifetime. The concept of the fusion ramjet, often called the Bussard ramjet, after physicist Robert Bussard, who proposed it in 1960, is elegant in its vision. Instead of carrying fuel on board, the spacecraft would scoop hydrogen directly from the interstellar medium as it travels, using powerful magnetic fields to funnel this thin cosmic gas into a fusion reactor. There, under immense heat and pressure, hydrogen atoms would fuse into helium, releasing tremendous energy that propels the ship ever faster. The beauty of this design is profound. The spacecraft becomes a perpetual engine, feeding on the universe itself, never running out of fuel as long as it continues moving through space. In theory, a fusion ramjet could accelerate continuously, gradually approaching significant fractions of a light speed. Unlike conventional rockets that must carry every ounce of propellant, the ramjet grows lighter as it accelerates, for it consumes nothing from its own reserves. Some calculations suggest that such a vessel could eventually reach 10, 20, even 30% the speed of light, reducing the journey to Alpha Centauri from tens of thousands of years to mere decades. A child born on Earth might arrive as an adult, still young enough to walk upon an alien world under foreign suns. But the universe does not yield its secrets easily. The interstellar medium, vast and seemingly endless, is not a highway of abundant fuel. It is a near-perfect vacuum, emptier than any void we can create in laboratories on Earth. On average, there is roughly 1 hydrogen atom per cubic centimetre of space. To gather enough fuel for continuous fusion, the ramjet's magnetic scoop would need to be enormous, stretching hundreds or even thousands of kilometres wide, an invisible net cast through the darkness, sweeping up atoms scattered across unfathomable distances. The engineering challenges are staggering. Creating magnetic fields of such magnitude requires energy, potentially more energy than the fusion process itself could produce at lower speeds. The spacecraft would face a paradox. It must already be travelling at tremendous velocity for the ramjet to gather sufficient hydrogen, yet it cannot reach that velocity without fuel. It is a cosmic catch-22, a threshold that current technology cannot cross. The dream of scooping fuel from space remains for now a beautiful mathematical possibility rather than a practical blueprint. Yet even if we cannot build a ramjet today, the concept reminds us that space is not empty. It is a medium, thin and tenuous, but real. As we journey through it, we do not travel through nothingness. We move through a sea of scattered atoms, ancient particles that have drifted through the galaxy for eons, witnesses to the birth and death of stars. To imagine a ramjet gliding through this cosmic ocean, its magnetic fields sweeping through space like the baleen of a whale filtering plankton from Earth's seas, is to imagine a vessel not separate from the universe, but intimately connected to it. Sustained by the very fabric of interstellar space, the ramjet represents a philosophy of travel where the journey and the environment become one. It is propulsion that does not conquer space, but collaborates with it, finding sustenance in the void. Whether or not we ever construct such a machine, the idea itself transforms how we perceive the distance to Alpha Centauri. Perhaps the challenge is not the lack of fuel, but learning how to harvest what already exists in the infinite spaces between the stars. If fusion ramjets represent harmony with the cosmos, antimatter propulsion is something else entirely. It is the harnessing of pure annihilation, the conversion of matter into energy with 100% efficiency. No chemical reaction, no nuclear fusion, No other process in the known universe can match the power density of antimatter. When a particle of matter meets its antimatter counterpart, both are destroyed instantly, transformed entirely into energy according to Einstein's famous equation, E=mc2. A single gram of antimatter combined with a gram of matter releases as much energy as a 20-kiloton nuclear bomb. An antimatter engine could theoretically propel a spacecraft to velocities approaching the speed of light itself. Calculations suggest that with sufficient antimatter fuel, a vessel could reach 50, 60, even 70% light speed. At such velocities, the journey to Alpha Centauri contracts dramatically. What would take millennia with conventional rockets, what would take decades with fusion ramjets, could be accomplished in just 6 to 8 years. A mission launched today could arrive before the next decade ends. Crew members could depart as young scientists and return as seasoned explorers, their lives measured not in generations lost to the void, but in years of purpose and discovery. The implications are profound. Antimatter propulsion transforms interstellar travel from a civilization-spanning endeavor into something almost within the grasp of human ambition. It is the difference between sending our distant descendants and sending ourselves. It reframes Alpha Centauri not as an unreachable abstraction, but as a destination we might actually visit, explore, and return from, carrying with us knowledge gathered from another star. But if antimatter is the ultimate fuel, it is also the ultimate challenge. Antimatter does not exist naturally in our corner of the universe. To acquire it, we must create it, particle by particle, using enormous amounts of energy. Currently, antimatter is produced in particle accelerators like those at CERN, where high-energy collisions occasionally yield antiprotons or positrons. These particles are then captured and stored in electromagnetic traps, suspended in vacuum chambers, prevented from touching any ordinary matter that would cause instant annihilation. The scale of current production is almost incomprehensibly small. Humanity has created only a few nanograms of antimatter in total throughout all of history. A nanogram, 1/billionth of a gram. The cost to produce even this minuscule amount is staggering, estimated at trillions of dollars per gram. To fuel an antimatter Starship would require kilograms, perhaps tons, depending on the design. At present rates, producing enough antimatter for a single interstellar voyage would take millions of years and consume more energy than all of civilization generates in centuries. Storing antimatter presents challenges equally daunting. It cannot be placed in any container. For the moment it touches matter, it vanishes in a burst of gamma rays. Current storage methods use magnetic bottles, trapping antimatter particles in fields that keep them hovering in perfect isolation. These systems are fragile, energy-intensive, and capable of holding only the tiniest quantities. Designing a storage system for kilograms of antimatter, one that could survive the vibrations of launch, the radiation of space, and the decades-long duration of an interstellar journey, is an engineering problem without current solutions. And yet, the physics is sound. Antimatter exists. We have created it, observed it, studied its properties. Unlike faster-than-light travel or wormholes, antimatter propulsion does not require us to rewrite the laws of physics. It requires only a profound advancement in our ability to produce, store, and harness it. The question is not whether antimatter propulsion is possible, but whether we will ever develop the industrial capacity and technological sophistication to make it practical. Perhaps one day, centuries from now, Antimatter factories will orbit the Sun, using its vast energy to produce fuel measured in kilograms rather than atoms. Magnetic storage systems, perfected through generations of iteration, will hold antimatter as safely as we now hold gasoline. Starships will depart from orbital stations, their engines glowing with the purest energy conversion imaginable, accelerating smoothly toward distant stars, leaving trails of light across the darkness. In that future, the journey to Alpha Centauri becomes routine, measured not in eons, but in years. Human lifetimes align with cosmic distances. The stars, once unreachable, become harbors in an expanding sea of exploration. But until that day arrives, antimatter remains what it has always been. A tantalizing glimpse of what could be. A fuel so perfect it exists only in fragments, reminding us that the universe's greatest gifts are often its most difficult to grasp. Both fusion ramjets and antimatter propulsion share a common truth. They demand technologies we do not possess, sciences we have not yet mastered, and perhaps most challenging of all, they require time. Not the time of a journey, but the time of civilizations. These are not propulsion systems for the next century, or even the one after. They are blueprints for a future where humanity has transformed not just its machines, but its understanding of energy, matter, and the fundamental forces that govern reality. To discuss fusion ramjets and antimatter is to acknowledge that reaching the stars is not merely an engineering problem. It is a testament to patience, to the slow accumulation of knowledge across generations, to the willingness to dream far beyond our lifetimes. These technologies exist today only as equations, simulations, and theoretical papers. They are ideas waiting for the world to catch up to them. And yet, in contemplating them, we prepare ourselves for the journey ahead. We learn to think in terms not of decades, but of centuries. We begin to understand that interstellar travel is not a destination we race toward, but a horizon we approach gradually, each generation adding their understanding, their innovations, their dreams to the collective endeavor. The fusion ramjet teaches us that space is not empty, but filled with potential. The antimatter engine teaches us that the universe's most powerful forces exist in the smallest interactions. Together, they represent the far future of interstellar travel, technologies that may one day carry our descendants to Alpha Centauri in years rather than millennia, transforming an impossible voyage into an achievable dream. As we ponder these distant possibilities, we realize that the journey to the stars is not just about propulsion or speed. It is about vision, persistence, and the unshakable belief that what seems impossible today may become inevitable tomorrow. In the silence of space, where starlight takes years to cross the void, we measure progress not in miles per hour, but in the slow, patient advancement of human understanding. And so we continue, dreaming of ramjets sweeping through cosmic hydrogen, imagining antimatter engines blazing across the night, knowing that somewhere in the distant future, these dreams may become the reality that finally carries humanity to another star. Beyond the mathematics of velocity and the physics of propulsion lies a question far more profound, one that cuts to the very heart of what it means to be human. Who will make this journey? And perhaps more importantly, can a human being, bound by biology and psychology, survive the voyage at all? The engines we have discussed, nuclear pulse drives, laser sails, fusion ramjets, these are triumphs of engineering, but they cannot solve the problem of time. Even with our most optimistic technologies, a journey to Alpha Centauri would span decades, perhaps centuries. And in that vast expanse of years, the human body and mind become not passengers, but obstacles, fragile vessels navigating an endless ocean of darkness. This is where the dream of interstellar travel confronts its most difficult challenge, not the stars themselves, but the space between them, not the destination, but the journey, not the technology we build, but the humanity we carry with us. A generation ship represents perhaps the most romantic and tragic vision of interstellar travel. Imagine a vessel so large it is essentially a world unto itself, a complete ecosystem contained within metal walls, traveling through the void for hundreds or thousands of years. The people who launch from Earth would never see Alpha Centauri, nor would their children, nor their grandchildren. Instead, the journey would be completed by distant descendants, people who have lived their entire lives inside the ship, for whom Earth is not a memory, but a myth passed down through generations. Such a ship would need to be entirely self-sustaining, farms to grow food, systems to recycle water and air with perfect efficiency, artificial ecosystems balanced so precisely that a single failure could doom everyone aboard. The ship would need schools, hospitals, governments, entire societies functioning in isolation. Births and deaths would mark the passage of time, measured not in miles travelled, but in generations lived and lost. The engineering challenges are staggering, but the human challenges are perhaps more daunting still. How do you maintain purpose across centuries? How do you ensure that the great-great-grandchildren of the original crew remain committed to a mission they did not choose? What happens when disputes arise, when resources become scarce, when people begin to question why they are trapped in this metal tomb, hurtling toward a destination they will never see? A generation ship is not just a spacecraft. It is a civilization in a bottle, sealed and sent into the darkness, with the hope that whatever emerges on the other side still remembers why the journey began. But what if we could bypass the problem of generations entirely? What if the crew that left Earth could be the same crew that arrived at Alpha Centauri decades later? This is the promise of cryogenic freezing, suspended animation, a concept that has lived in science fiction for a century, but remains tantalizingly out of reach in reality. The idea is elegant in its simplicity. Cool the human body to temperatures so low that biological processes essentially stop. Metabolism ceases. Aging halts. The passengers sleep, preserved in stasis, while the ship continues its journey through the void. If perfected, cryogenic suspension would transform interstellar travel. A journey that spans 50 years could feel, to the crew, like a single night's sleep. They would close their eyes in orbit around Earth and open them in orbit around Alpha Centauri, unchanged, unaged, the same people who began the voyage. Yet the challenges are profound. No human has ever been successfully frozen and revived. At temperatures near absolute zero, ice crystals form in cells, rupturing membranes and destroying tissue. Current research explores vitrification, a process that transforms bodily fluids into glass-like states without crystallization. But we are far from applying this to whole organisms, let alone humans. Even if we solve the technical problems, questions remain. What happens to consciousness during suspension? Is it sleep, or is it something closer to death, a cessation from which we may or may not return as ourselves? And what of the psychological impact upon waking? To sleep for decades, and wake to find that everyone you knew has aged or died, that the world you left no longer exists, that you are, in every meaningful sense, a traveler through time as much as space. But perhaps the most radical solution is to abandon the human body altogether, at least temporarily. Instead of sending living people, we could send the information required to create them. Imagine a probe, small and fast, carrying within it the genetic blueprints of humanity. DNA sequences stored in crystalline matrices, stable for millennia. Alongside them, artificial intelligence systems capable of autonomous operation, construction, and perhaps most extraordinarily, the creation of life itself. Upon arrival at Alpha Centauri, these systems would activate. Robotic constructors would harvest materials from asteroids or planetary surfaces, building laboratories, habitats, and life support infrastructure. Then, using the genetic data carried across the stars, they would synthesize human embryos, gestate them in artificial wombs, and raise the children in a carefully constructed environment. These would be humanity's children, but they would be born on another world, raised by machines, inheritors of a legacy they never witnessed. They would be, in a sense, the first true children of the stars, not travelers, but natives of a distant sun. This approach eliminates the need to keep fragile biological organisms alive for decades. It reduces the mass of the spacecraft dramatically, allowing for faster transit, but it raises profound ethical and philosophical questions. Are these children truly human if they are raised by AI? What culture, what values, what sense of identity would they possess? And do we have the right to create life in such isolation, so far from any possibility of return or rescue? Yet even these approaches assume that human biology in some form must make the journey. But what if consciousness itself could be separated from the body? Digital consciousness transfer represents the most speculative and controversial solution to interstellar travel. The concept suggests that human minds could be uploaded into digital substrates, transformed from biological neural networks into patterns of information that could be transmitted or carried aboard spacecraft as data. A digital mind would not age, would not require food or air, would not suffer the psychological strain of confinement. It could inhabit virtual environments indistinguishable from reality, or it could interface directly with robotic bodies upon arrival, experiencing the new world through mechanical senses designed to perceive far more than human biology ever could. But this raises the deepest question of all. If a copy of your mind travels to Alpha Centauri, is it still you? If consciousness is information, can it be copied? And if so, which copy is the original? The question of identity becomes not philosophical speculation, but practical necessity. Are we sending humans to the stars, or are we sending echoes of humans, ghosts in the machine, wearing the memories of people who remain behind? The psychological challenges of interstellar travel extend beyond technology. They reach into the core of human experience: isolation, confinement, the knowledge that you will never again see Earth, never feel natural sunlight, never walk on grass or breathe air that was not recycled 1,000 times. Astronauts on the International Space Station report feelings of profound isolation despite being only 250 miles above Earth, despite being able to see their home world through the window. What would it feel like to watch Earth shrink to a pale blue dot, then to a distant star, and finally to disappear entirely into the background of countless other stars. The human mind evolved on vast African plains, under open skies, with horizons stretching to the edge of sight. We are creatures of space and light. To spend years, decades, or lifetimes in the confined corridors of a spacecraft is to live in a way fundamentally opposed to our nature. And yet, perhaps, this is the ultimate test of humanity. Not our ability to build faster engines or more powerful weapons, but our capacity to endure, to adapt, to carry the flame of consciousness across distances so vast they defy comprehension. But there is another possibility, one that is becoming increasingly likely as we develop more sophisticated artificial intelligence and robotics. Perhaps the first emissaries to Alpha Centauri should not be human at all. Machines do not age. They do not require food, water, or breathable atmospheres. They can withstand radiation levels that would kill a human in minutes. They can be repaired, upgraded, and, if necessary, rebuilt from raw materials harvested along the way. Most importantly, they can wait. A robotic probe could spend centuries in transit without concern, arriving at its destination ready to explore, analyze, and report back to Earth. The first visitors to Alpha Centauri might be artificial minds, silicon explorers carrying our curiosity, but not our biology. They could survey worlds, assess habitability, and perhaps even begin the process of preparing environments for eventual human arrival, if such arrival ever becomes feasible. This raises a question that may seem radical, but is worth considering. Do humans physically need to make the journey at all? If our robots can explore, if our AI can analyze, if our probes can transmit data back to Earth, perhaps the true journey is not one of bodies, but of knowledge. Perhaps we reach the stars not by going there, but by extending our senses and our understanding across the void. And yet, there remains something deeply human in the desire to go, to see with our own eyes, to stand on an alien world and know that we have crossed the greatest ocean ever contemplated. Exploration is not merely about gathering data. It is about presence, about the profound act of being somewhere, of experiencing it directly, unmediated by cameras or instruments. If we do eventually arrive at Alpha Centauri, whether as biological beings, digital consciousnesses, or reconstructed genetic descendants, we face yet another challenge. What then? The journey is only half the story. The destination must become a home. Terraforming a world, if such a world exists in the Alpha Centauri system, could take millennia. Transforming an atmosphere, seeding microbial life, gradually building an ecosystem capable of supporting human existence. These are projects that dwarf even the journey itself. We would arrive not as colonists moving into a prepared home, but as architects beginning a construction project that our descendants 10,000 years hence might finally complete. The question of interstellar travel, then, is not simply, how long would it take? It is, who will go? What will they become? And when they arrive, will they still be us? In the darkness between the stars, humanity confronts not just the limits of technology, but the limits of itself. And so we return from the edges of possibility to the question that has guided this entire journey. How long would it truly take us to reach Alpha Centauri? The answer, like the cosmos itself, contains multitudes. With conventional chemical rockets, the technology that carried us to the Moon and Mars, the journey would span 73,000 years, longer than all of recorded human history. Entire civilizations would rise and fall in the time it took one spacecraft to bridge the gap between stars. With nuclear pulse propulsion, riding the shock waves of atomic explosions, we could reduce that time to perhaps 100 years. Still a journey no single generation could complete, but one that falls within the span of human memory and planning. With breakthrough Starshot, propelled by Earth-based lasers pushing gossamer light sails to 20% the speed of light, we approach something extraordinary. A probe launched today could reach Alpha Centauri in just 20 years, sending back images of alien worlds within our lifetime. This is not fantasy. This is engineering already in development, funded by visionaries who understand that the impossible is simply the untried. The most realistic scenario for humanity's first touch of another star is not grand. It is small, elegant, and profoundly achievable. Within this century, perhaps within the next few decades, a fleet of tiny probes, each no larger than a smartphone, will be launched into the void. Propelled by light itself, they will accelerate to speeds that would have seemed like magic to our grandparents. 20 years later, as those probes cross the threshold of Alpha Centauri's light, they will transmit images across the darkness. 4 more years for those signals to reach Earth. And then humanity will see, for the first time, the shores of another star. For humans to make that journey, the timeline stretches further. Generation ships, vast vessels carrying entire communities across the centuries, or suspended animation technologies that place travelers into a sleep deeper than dreams. These are the pathways for human voyages. Such missions are likely centuries away, waiting for technologies we can barely imagine and resources we have not yet gathered. But they are not impossible. They are simply not yet. Each generation of humanity pushes the boundaries further than the last believed possible. A century ago, we had barely left the ground. 50 years ago, we walked on the moon. Today, we plan journeys to distant stars. What seemed like the domain of myth becomes, slowly, inevitably, the work of engineers and dreamers working side by side. The journey to Alpha Centauri teaches us something profound. It is not merely about reaching a destination. It is about the transformation that occurs along the way. Every equation solved, every material tested, every theory refined. These are not just steps toward the stars. They are reflections of who we are and who we are becoming. A species that looks up, that reaches beyond, that refuses to accept that the cosmos is forever out of reach. The first steps to Alpha Centauri are not being taken in distant futures. They are being taken right now. In laboratories across the world, scientists test laser arrays and design light sails. Engineers model fusion reactors and antimatter containment. Physicists explore the boundaries of propulsion and the limits of physics itself. The journey has already begun. We're not merely observers of this cosmic story. We are participants. The time frame to touch another star is measured not just in years, but in choices, in curiosity, in persistence, in the collective will of a species to reach beyond the familiar darkness and touch the light of distant suns. If this journey has sparked something within you, a sense of wonder, a question about what lies beyond, then share that spark. Like this video, comment below, and let us know where in the world you're listening from, and subscribe to join us as we continue exploring the vast, beautiful mysteries of our universe. The stars are waiting, and for the first time in human history, we are learning how to answer their call.